It's kind of long, but what it's about is closing the loop on walking. That's really the main bit of this. And the first steps is to tell you that it's preliminary stuff, to put that caveat on there. And then the other bit's telling you kind of what we're going to try to close the loop on. And that's going from human walking data in some way, shape, or form. It's still cursory what we're doing, preliminary, but that's what we're going to do, to hybrid system models, to robotic walking, and then go back and do a comparison with the human walking, at least at a course level. And I'll explain all that during this talk. And yeah, as announced, I'm Aaron Ames. I'm at Texas A&M. And this is joint work with my grad student, Ryan Sinet, who has a poster later you should stop by. So let's get started, huh? So throwing up a bunch of pictures. Now, usually when I give this talk to an audience not full of experts on this, people don't know all this stuff. You guys have seen all these bipeds before to some degree. What I consider, with this research, the main challenge is to obtain human-like bipedal robotic walking. What that means, how we quantify that, those are still open questions in my mind. But that's kind of where I'd like to get eventually. All right. People have know some of these walkers. These are just pictures of random walkers. None of these are mine except for this one, which is not really working. So that should tell you that I'm coming from the theory perspective here a little bit. A nice SolidWorks model is what I'm going to give you. Eventually, I'd like to have a picture of a real robot that walks next to these, but that's not now yet. So what's the idea? The challenge is human-like walking. And the idea is to use human walking data to try to motivate the construction of hybrid system models, meaning the mathematical framework that you're going to use to model the system. And in addition, motivate the construction of controllers. Okay, so it's kind of a two-pronged approach. We'd like to really fundamentally understand walking from this perspective. Okay, so in this talk, what we're going to do is we pull a little bit of data from this book, Biomechanics, by Winter, and we're going to do some things with that data at a basic level to construct a hybrid model that we'll consider in the context of a robot. So I'll get into more of that later. First, a little bit of history. Now, this is another one of these slides that usually when I put this up, people haven't really seen these things before, so there's no explanation. Of course, in this audience, everyone knows what this is. That's, usually people don't. Yeah. Really? People? What do you think? That? Yeah. That's a passive dynamic walker. It's McGear's walker. It's not, right. Though. Well, it's our copy of McGear's walker. Is that your copy of McGear's? Yeah. Oh, bad. That's what happens when you have experts in the audience and put the wrong pictures on. But I do have this, and this is definitely McGear. For people that, I'm sure everybody's seen this, but this is his actual, you agree that this is McGear? All right. That's McGear right there. And this is his walker. And everybody knows that this works. This is not completely, he adds some initial energy to it. He has knee locks, knee stops on this walker to prevent them from bouncing back. What he called knee bounce, which I've actually studied a bit as well, but that's not in this talk. But what I like is the look on his face when this thing goes. A big smile, right? I guess that's the plus of seeing everything come together. Kind of how I feel when I prove a theorem, but nobody gets to see me smile on video. All right, and then now this, we know what this is, right? Yeah, this is the Collins biped here, Collins is somewhere here, I assume, or maybe not. All right, well, he's not here, but this is the Collins biped. So the whole point here is really the whole dynamic thing kind of started with McGear, right? Everybody knows this. And this Collins biped really tried to capture some of this passive dynamic ideas with some basic control, with some minimalist control that would allow for walking on flat ground. And I think everybody's seen this thing go if you're sitting in the audience and you're at this conference. So I won't go into a lot of detail there. But the idea of this, I think, is very important, and that's to capture the inherent nature of walking and mechanisms with relatively small and minor control, okay? That just ties into that nature. And then lastly, I have up here the talk we saw the first day, Jesse Grizzle's Mabel.
That's actually Andy's copy of Mabel.
See, that I know is not true, but all right. That's very good. So we all heard what Jesse did with this. And that's with these hybrid zero dynamics and a lot of really good theory. They came together with some very impressive walking. We saw how robust it was to perturbations and everything like that. So to me, this is a lesson that if you really understand a basic framework in which to achieve walking, you could do it on a variety of mechanisms and hopefully more and more complex mechanisms. So he's done this on 2 bipeds. He's now studying 3D and on from there. Now, when I say history here, this is not a comprehensive history, as everybody knows in this audience. I'm just pulling out the main points that are important for this talk. Okay, let me put that caveat in. All right. So what are the lessons from this, though? What are the lessons of the success of these different methods and their failures? Because, for example, with the Collins walker, it worked for a while, right? And then they tried to make it a little bit more robust, and it stopped working. So what does that tell you? It tells you that if you don't really understand the fundamental mechanisms of walking, you can't repeatedly get walking on different mechanisms, right? And you can't improve their robustness. So really the goal here, the motivation is if you can, again, understand these fundamental properties of whatever that means. This is a very philosophical statement here, right? Then you can do things like achieve human-like walking, if you really get walking, right? And you can do it on a wide variety of systems. And I don't just mean bipeds. I mean prosthetic devices, everything that we've been studying or been talked about in this conference. All right, so that was the motivation. Now, what do I do? Because we haven't really gotten there yet. And what's my sort of big picture approach, right? And I like, all right, I'm coming from abstract math in my graduate, so I love commutative diagrams, if anybody gets this reference. But basically the idea is, this is what you want to do. You want to close this loop, and this is the loop on walking, all right? So what you want to do is start out with efficient human walking as your motivation, okay? And from this walking, you want to understand how to model systems, how to model robots, okay? So in the case of a robot, there's lots of choices you can make on its model. How many different phases of walking are there, everything like that. So you want to make those decisions based on the human walking to get these models. Once you have these models, you want to do, obviously, control. I'm a feedback control person, so for me, this is feedback control to get to bipedal robotic walking, all right? And you want to do some analysis on that walking once you get it. What's the domain of attraction? Is it stable? All the things that we've talked about there. Once you kind of get this stuff down really well, you can use this understanding to do things like design really nice prosthetic devices, okay? Because we already know how walking works, so when we know that, we can help people walk better, improve their efficiency, right? And we've already seen that people with prosthetic devices tend to have lower efficiency in walking, so we want to make that better, make their quality of life better. And so what that should do is if you do proper design on these things, you should get back to efficient walking, right? And close that loop. So that's kind of the big picture. Now what do I do in this talk? I don't do all that in this talk, all right? I'm going to talk a little bit about this idea of modeling hybrid systems from human data, okay? Just some basic markers that you can use to come up with these models. And what are hybrid systems? So one thing is I'm also coming from a theoretician, formal background, so I've done a lot of, I like formal mathematical models whenever I can get them, all right? So by hybrid system, I mean a formal model with continuous dynamics when the biped's swinging forward, discrete dynamics when feet touch the ground, when the number of contact points change, things like that. And hybrid dynamics is when you combine these in a coherent framework. All right, so what do we do for our actual control then? Once we have the model, we're interested in making walking. So our idea here is to use human-inspired controllers in some sense. I'll explain that later, to do two things. The first thing we do is we study the 2D walking. So we consider the sagittal restriction of some 3D biped, all right? And what we do is we use passivity-based design, because I think it ties nicely into the inherent walking that's present in bipedal mechanisms. And we couple that with some human-inspired controllers, things like trying to get the toe to push into the ground and lift off, to get sagittal walking. Once we have sagittal walking, we use this sagittal walking with reduction, which had been talked about in a variant by Bobby earlier in this conference, to decouple the dynamics of the system, respect the sagittal walking, and then finally we use input-output linearization, which is essentially hybrid zero dynamics, only we don't have the hybrid part on there, to get to the conditions where this is satisfied. And the end result of all this, sort of approach is that we should get 3D walking for complex bipeds, okay? And we get up to 10 degrees of freedom in the model we're going to study here, which is not bad, not great, but not bad. I mean, we could do better. All right, so let's go to what might be the interesting part to some. And again, biology, all these kind of people coming from really understanding human walking, I want your feedback on these things, because this is not my, my original area. So I'm trying to work with things like this. So what do? We start with human data, like I talked about. We use the constraints on the human data, things like when the toe's down, the heel's down, to come up with these hybrid models, okay? Once we have a hybrid model, we consider a biped, and we try to map this model onto a model of the biped, okay? So the idea is we're getting this model for the biped not by just guessing, not by picking the easiest thing in terms of theory, but by what best accurately represents what a human does throughout its gait, okay? So let's talk about that, but first I had to have one slide with a bunch of math, just because, all right? This is the definition of a hybrid system, all right? I've used this slide about 50 million times. But what do we need to understand from this definition? If you don't like math, don't read the math, listen to what I'm saying. What do we need to understand? Well, a hybrid system, or in this case a hybrid control system, consists of some basic things. First of all, you have an oriented graph. This tells you the discrete structure of your system and how it evolves, okay? So you have a number of domains, or if you like the walking term, phases. You have these discrete phases that are in a system and edges that tell you how you transition from one phase to the other.
Can we say state machine?
It's a state machine, yeah. It's an autonomous state, yeah. All right, so on each vertex of this graph, or each state of this machine, you have a domain. The domain is like your configuration space, okay? Or actually your phase space. It tells you how the system can evolve, okay? Without dynamics yet, all right? You also have a set of controls that tell you how you can actuate the system, right? You have a set of guards. Now what guards do, or you can also call them switching surfaces, they tell you when you switch from one domain to the other. These are spatial constraints, okay? These are not temporal, but they're spatial. So for example, the height of the foot. When the height of the foot gets to 0, you're going to transition to a domain where the foot's on the ground, okay? Reset maps, also called impact equations in this area, just tell you how your states change once you go through an impact, okay? So you can spend a lot of energy just how do you come up with these? It's a very complicated question for lots of systems. Finally, we have dynamics on each domain. This is some control system or vector field that tells you how your system evolves on that domain. All right? Now, we can also consider hybrid systems, which are simply hybrid control systems without any control.
Questions in the example you've shown, the continuous dynamics as explicit. Can you include implicit dynamics as well?
You can, yeah. I don't, because I don't need to, but you can.
Can you translate that? One or two of you translate that question.
What? Oh, he's asking if you can come up with more, maybe have some surface you need to stay on, for example, right?
For example,
yeah.
the closed kinematic chain you get with both feet on the ground
right.
is intrinsically implicit dynamics. You can't write it explicitly.
Yeah, actually, so yeah, in that case, we actually need to consider that. But what we do is we enforce that closed chain through holonomic constraints. So we actually have dynamics plus constraints, which we often do. Okay, but yes, you can do implicit as well. So that's not a problem.
Another question. It seems to me that this description is in the eye of the beholder, the observer. It's not a property of the system.
What is certainly a property of walking?
Oh, that's not clear.
That's like saying the description x dot equals f of x is in the eye of the beholder for understanding dynamical systems. Well, it's a mathematical representation of these systems.
I think Chris was only halfway through his question.
Oh, all right, sorry. Go ahead, continue on, please.
Okay.
Yeah.
It seems to me what you're doing is you're looking for discontinuities in the dynamics, and you're representing the dynamics with different functions on different sides of the discontinuities. If I do discrete time dynamics, which often makes it harder to detect the discontinuities, and I throw everything into a big lookup table, so I'm not writing it out in code or equations. These various, the discontinuities, the domains, it's very hard to find them in the big lookup table.
Agreed. Yeah.
So it seems that this is a property of your representation. It's not a property of the.
I mean,
you can take it the other way. For small enough time steps, everything is continuous.
Yeah, you could do the same thing too, where the impacts actually we represent them as being instantaneous. But no, listen. There's multiple representation. There's reasons why we pick this representation though. Just like there's reasons why you might pick a discrete representation. Okay. We want to do control first of all. Okay. We can model these systems on each phase. But continuous, Newtonian, whatever, equations to get nice dynamics that represent how the robot evolves over time. So that naturally fits within this context. It's just what you would do if you're going to drop a ball. You could do a discrete representation of it at different time steps, or you could just model F equals ma, right? And get a mathematical model for the ball falling that again, is not exactly in tune with reality, but it's very, very close. Right?
I think we could cut this short. Between the word system and is, you put the word model.
Yeah. And I use model a lot of places here, right? There, let's do that. Yeah, let's not dwell on the modeling. That's actually a good point. But we can talk more about this. But this is the representation we choose because it does make sense in this context. All right. So now let's get back to bipeds here. Now this model, again, there's a lot of choices here. We have graphs here. So for example, how do you pick the right graph for a biped? Okay. Well, we've seen this quite a bit in this. This is a compass gait biped. Everybody's seen this forever now, and it's really well understood, and it's a great example to start with. This is a hybrid system with a single domain and a single edge, right? So when the foot strikes the ground, you switch, okay? But as you build up the complexity of your biped, you get more complex hybrid models. So if you start adding a knee, let's say, and if this knee locks, like it did in the McGear one that we saw, then you actually get a hybrid system with this kind of discrete structure, where you have this knee locking event that occurs. After that, you have a straight leg. Then the foot strikes the ground, and then the leg bends, okay? And you can actually consider combinations of this even on this model. You can start to say, well, let's say the knee never locks, then you might have another loop here that says the knee doesn't lock, and then knee locks, right? So even here, you start seeing that there's some choices in the model you can make. By assuming knee locking, we're assuming that the knee actually gets to that knee lock position, okay? Now, as we build up the complexity of the biped, so here we have a biped with feet and knees, we get more and more choices as to what the hybrid model can be. So in this case, here's two of ones that we've actually studied, both of these, and got walking for them. But I'm going to talk about this one in this talk. But basically, two possible choices of discrete ordering of events, when they occur, how they occur, what occurs. Okay, so we have things like heel strike, toe strike, and we pick that order. Okay? So again, there's all these choices. And again, we sat down when we first started doing this stuff, wrote down these things with like 16 domains, and it got really crazy. So how do we pick the right representation? Okay, so that we're, again, with some objective. And the only objective that I can think of here, or the main one I want to think of, let's put it that way, is human motivation. Let's look at humans to decide how to pick these models. Okay? So here's the winner's book. Here's the data that you get from the back from his motion tracking, his human with all his measurements and everything like that. Let's use this to come up with this discrete structure for the hybrid model. So use human motivation. Okay, so let's start out. This is actually the walking that was recorded in that book. All right, and I'll play a movie for you. This is just us taking the data from the book and putting it into a simulation. Okay, so this is a human walking. It's actually pretty fast walking. And if you try to determine what's happening here, this ordering of events and everything that's going on, it can actually be a little bit difficult just from looking at this. But the knee never really locks. It kind of locks, and then the human sort of does a little bit of this on the knee. There's lots of complicated stuff going on with this walking. All right, so how do we break this down into a way that we can construct a model from it? All right. So the main thing we're going to do is look at our different constraints for the system, okay? So if you think about it as a model of floating in space, how do you enforce the fact that the foot's on the ground? Well, you can have a holonomic constraint for the foot, right? So let's look at those constraints, which are just the height of the foot, and look at what they look like for the human. Now, in this region, it looks like the foot's on the ground, because both the heel and the toe are on the ground, okay? So in this region, we'd want to be in one of those discrete events where the foot's on the ground, okay? And then, so this is the first leg, and this is the second leg. So what we're basically going to do is look at this data, look at points when the constraints are enforced, first when they're active, and then when they deactivate, okay? And we're going to write these down. All right, so the knee actually never locks for very long in a human. Although, actually, this is up for some debate because, you know, when the human may not have a completely locked knee, but muscle tension and everything like that, I think, is essentially equivalent to a locked knee in a robot. So we actually end up putting a locked knee on a robot, but that's a different story. But we have things like, during the course of the gait, the heel is on the ground for this long with the human. The toe is on the ground for this long on the first leg. Okay? The second leg, heel, toe on the ground. Okay? So once we get that discrete breakdown of events, we can actually project it to a hybrid model. Okay? So basically, at every point in time, we look at how many constraints are enforced. So in this case, we're on leg 2, and we have heel and toe down, which means the foot's flat. Right? And then the next event that happens is only the toes on the ground. So we actually get heel lift, right? You can go through, and this is, by the way, over the course of 2 steps, because you need basically 2 steps, one leg, then the other leg. Then you're back to when you start. That's why I only pulled out the data from the first half of the gait, because this will repeat, okay? All right, so what we've done here is actually take the human and gotten this hybrid model when you break it all down. Okay, we have our events, we have the different configurations of the human in these discrete phases, and the different events that happen transitioning between phases. Okay? So that's our human model that we basically want to use to motivate the model of a biped. So now let's go to robots, which is what my interest is. Okay? And we start out with this robot. Again, we have knees, we have feet, so how do we construct the hybrid model? How do we choose the ordering events, the temporal ordering? Well, we're going to kind of use the human as motivation. All right? So we're going to use human data to go to this biped. So we start out with the human model here. Now, we're going to make a couple choices. We changed a couple things here. Because obviously, all humans walk differently. There's no notion that this is a universal model. Many of these events are actually very close to each other. Okay? So we can do some reordering, and it still doesn't really disrupt things too much. So the first thing we actually did is we switched heel lift and knee strike. This is something that seems rather variable. Okay? But that's the only ordering switch that we did. The second thing we did is you see the human never completely locks its knee. It just has a knee strike. And we actually, with the robot, want to do knee lock because we don't want to do all the actuation that's needed to keep the knee slightly bent. Okay? This is our robot model. Again, same number of domains motivated by the human. Okay? So once we have this discrete structure in place, coming up with the entire model is actually very easy. It's just doing basic modeling. Okay, well, relatively easy. So we take this as our discrete graph for our model. We have on each one of these things, we have configuration spaces on each domain. And we're doing a 3D biped, so we have coronal angles, or lateral angles if you prefer. And then what we do is we piece all this together on each domain. We get control systems. Okay? Again, all these details aren't important. The point is we're getting this mathematical framework. Finally, we get all the impact equations that occur. Now, the impact equations use a bunch of different constraints, and it can actually be quite complicated to come up with these. But for this, there's a lot that's been done on this, and Jesse and I worked on some of this recently with Christine, who is really good at this stuff. Christine really is the one that did a lot of the main modeling stuff to try to understand how to better do these things. So that's a story in and of itself, but that's not this talk. All right, so let's talk about walking now that we've got our model, because I think that's what everyone's interested in. Okay, so what we're going to start with is 2D walking. Okay? And the main idea is to use passivity-based control, because it seems to work pretty well for obtaining natural walking, whatever that means, and human-inspired controllers along with it. Okay? So the first thing is because we're studying 2D walking, all right, we have to restrict our biped to a 2D walker. All we do here is something called sagittal restriction, where we take our hip and we basically hold it constant. So it's like we add this support boom to our bottom. Okay? And that results in a two-dimensional model for the biped. Okay? We're going to start here. Now, our controller actually uses 5 different controllers. And this is a lot of text, so you don't have to really read it. I don't read text on slides very much, so I don't blame you. But look at the picture if you want. Basically, what we do is we tie into this actuation structure. Okay, there's been some discussion on actuation, under actuation versus full. Some people restrict to under actuation only, which makes things more difficult. Some people do full actuation because they want to do a little bit more elaborate things. So we actually respect the actuation structure of the biped here. Okay? And we actually do different controllers depending on whether we have full or under actuation. So we're being physically, at least in this case, we're trying to tie to physical reality in our controller choice. Okay? Pointing out these differences. So I'll explain this a little bit more.
So Aaron,
yeah.
So in the full actuation case, does that mean you can apply a torque between the toe and the ground, or just at the ankle? Excuse me.
No, in the full actuation cases at the ankle.
Just at the ankle.
Just because the foot's flat.
Right.
Okay? And that's the whole point. Actually, you look, what makes these full actuated is the foot's flat. That's really the key distinguishing point.
And over-actuated doesn't mean
No, we don't worry about that. Yeah. All right. So now first, I'm going to introduce the basic controllers that we do. I'm going to be kind of high level here. If you want to look at the math, you can. But the first thing has kind of been discussed, controlled symmetries, which is Spong and Bülow. Spong right there did this, what, like 15 years ago, about-ish, 10 years. All right. 10 years ago, they came up with this idea that, well, we get this nice passive walking down slopes. If you apply this this group action to the system, basically, you can develop a controller that just shapes the potential energy, because this is actually invariant under this group action. You can get walking down on flat ground that mimics the walking down a slope. Okay? The good thing is that this gives actually pretty nice looking walking, because it's passive based. It's passive based walking. And this is actually an example of a kneed biped without feet that we did a while ago. But you can see this is the 2D walking that we get just applying controlled symmetries to this biped. It looks pretty good. Again, we were making the assumption of full actuation. The problem with control symmetries is that it requires full actuation. So here we were actually actuating the ankle even though we don't have feet, which was not very good. Yeah?
So I don't understand why you say it looks good because it's passive.
I'm not saying it looks good because it's passive. I'm saying that passive, I think, is out of the choices we can make of controllers, one that ties into the inherent walking of the mechanism better than most. That's what I'm saying in a longer statement, if you prefer. The fact that you can walk down a shallow slope without any actuation tells me that passive walking is in some sense tying into the natural ability of bipeds to walk. Okay? The structure of us.
But
all right?
for example, because this thing has no feet,
Yeah.
it's actually not very human.
Of course not. I just said this is a very old model. That's why we added feet.
When you put feet on it,
Yeah.
at least as far as I know, you know, to say our guide it has to be passive on.
Let me show you what we do with feet.
Okay, good.
Because again, this was without feet, and that doesn't make it good. I completely agree. So we added feet. All right, and that's what this talk is about. We have feet the whole time. This is not our model for this talk. It was just to show the concept. Now, the other thing that we actually do is on the under-actuated domains, we actually do this sort of partial controlled symmetries, where we apply controlled symmetries wherever we can, and we don't otherwise. So we kind of keep the actuation going, even though that won't result in walking by itself. That's our second control law. Now, our third control law is a spring damper. I don't feel like I need to really describe that to you guys, but we add spring dampers to the system.
And those are joint by joint, not some matrix things.
Actually, what we're adding, we're just doing it on the ankle right now. We don't do compliance here. We want to do compliance, but we don't do compliance right now, really. We just add a spring at the ankle to basically prevent the foot from rolling around. Pretty straightforward. Okay. Now, the last one. This is the most interesting controller from a sort of human-inspired perspective. Okay, is that we have this discrete structure breakdown to our system. All right, and we want to try to affect the same transitions that model has, but obviously those won't necessarily happen in that order. So what we actually do is we look at the Lagrange multiplier associated with a constraint, and we try to zero it. Okay, so if the heel's on the ground and we want to get heel lift, we look at the Lagrange multiplier, which is basically the normal force associated with that contact, and we try to zero it to get the heel to pop up. Okay, and what we do in this case is a time controller. Now, we know time controllers aren't robust. In fact, we saw that this wasn't a very robust controller. So we've done stuff since that's not in this talk yet because it's still getting fine-tuned, but we've gotten walking with controllers that are not timed. You can actually make this a function of space. But with some, in fact, Jesse suggested some of this to us on ways to do this. But the whole point of affecting the Lagrange multiplier, I think, is a really good idea to affecting these transitions, because then you know the transitions are happening when you want them to, because this is the condition that this be 0, that the transition actually happens. So you're enforcing the transition condition. All right. The last, yeah.
You're effectively controlling the 0 moment point.
Yeah. That is what you're doing. You're moving it forward. Yeah, exactly.
Moving it to
it's like all those the other points that you consider to try to move things forward. It's very equivalent to try to get the heel lift and things, moving the ZMP forward. All right, so the last controller is that there's always a problem with scuffing. People that have done bipeds a lot see this problem. So what we actually do is we add a last controller that's sort of virtual gravity, that repulsive force that pushes up the closer the foot is to the ground when it's swinging. So that prevents the foot from banging into the ground and kind of keeps the foot up.
And you had that in your last model that you didn't tell us about without the foot that you showed the video.
I didn't have this in that. I didn't have any of this in that. No. Okay. That actually scuffs the ground very lightly, but we just ignore it, which is a very common thing, right? To kind of pretend it isn't there. All right. I better get rolling here. So now, how do we combine these controllers? Well, we have 5 different controllers. Now let's kind of go over the big picture here. We have on our fully actuated domain here, because we're fully actuated, we do controlled symmetries as our main controller to put a lot of energy into the system. Then we have a spring damper controller, which will be on every domain, so I'll stop talking about it to keep just the spring at the ankle. And we have a scuffing prevention controller. So we do that because we want the swing to swing forward and then the foot not to hit the ground, right? Pretty straightforward how we pick that. Now, the interesting thing is we keep doing this basic strategy, but I'm just going to kind of point out our last controller is the lambda zeroing. Okay? So in this domain, the foot's flat on the ground, and what we want to have is heel lift. So what we actually do is we consider the Lagrange multiplier for the heel. We try to send it to 0. Okay? And we do that effectively to get the heel to pop up. Okay? Then in the next domain, we actually keep that controller going to get the foot rotating, to keep the foot rotating off the toe. Okay? Then we have heel strike. So we have a toe up and we have our heel down here. At this point, we have to kind of think about toe lift way off here. So what we actually do is we try to do a push off like humans do. Okay? So the first thing we do is we take the Lagrange multiplier for the back toe and we.
Why can't you just say force
What do you mean?
instead of Lagrange multiplier? It's just,
okay, force.
I mean, I think
force. Yeah,
for some fraction of the audience, the word force.
Force. Let's call it force. Okay, the normal force. Okay, that we're affected. All right. So we look at the normal force at the toe, and the first thing we do is try to push into the ground and make that bigger. And then the next domain, we actually let up on that force to pop the toe up. So we kind of try to do this thing where humans do, where you sort of push into the ground and then lift up, okay, with the force. So in the end, that's how we kind of combine all these controllers, all right? And the end result is we get walking, okay? And I'm going to, with choices of gains and all that kind of stuff, all the details, but this is what the walking looks like. Now, I don't think it's that bad. I think it could be better.
What's the forward speed?
I'm not even sure off the top of my head. I don't think we've actually computed. Ryan, do you remember what it was?
Well, the video is not real time, first of all.
It's not exactly real time. It's
continuous.
close.
Like each
It's
frame
close.
is a specific amount
Yeah.
of time. So
But what was the speed? I don't even remember. We computed it at some point, but I don't. Speed wasn't our objective, so
Yeah.
it's
Again, what Chris is saying is passive robots walk slow.
yeah. I mean, it's reasonably slow, but not super slow. Is what I remember on the speed. I don't remember the number off the top of my head. I'm sorry. This was like we actually did this and computed the number. It was a while ago.
Speed is whatever
It's whatever the slope is. The thing is, you can actually adjust the speed, and this is part of the reasons why we don't actually compute speed. Is as you change the virtual slope, you get faster walking. The trade-off is that as you get a steeper slope, you go more towards instability. And at some point, you start getting bifurcations, which we talked about, right? The steeper slope, more bifurcations. So you have to be careful. You can only get so much speed out of this. But you can actually get reasonable speeds out of controlled symmetries. It's the same as with any controlled symmetries. The variation of speed depends on the slope. I can compute that explicitly for you if you want, but that wasn't really our
it's
objective.
going to be around 0.7
Right?
plus or minus.
Okay. I believe that.
Seconds,
Yeah, I believe that.
Yeah. That's true.
But again, our objective here is not necessarily to walk at any given speed. It's to walk nicely, whatever that means. All right. Now, I'll talk about that more later. But all right, so I just wanted to show you the graph of Lagrange multipliers to show that we're doing the right thing, or the normal forces at the contact points, if you prefer. So basically, this is the heel. What we do is we actually zero the heel to get heel lift at this point, and then we keep pushing the heel forward to rotate forward. This is the toe, and what we do here is we first push the toe into the ground, then we take off that force to lift the toe right there. Okay? So you can kind of see it's lining up nicely with what we wanted to have happen. These are the phase portraits. They're closed loops, which is what we want, right? That's really all we care about right now. And here's kind of an initial stab at this. I'm gonna talk about this a little more later. Human walking with a question mark here. We actually took with this model and compared it with some data from Ackerman, and he actually let us use this top part of this figure, thankfully. And we did this comparison of the double support phase in the human, which has been kind of underrepresented, I think, a lot of the literature is the importance of double support. And the human spends, 24% or 76% of its time in double support? It should be the other way around. Yeah, that's flipped, my bad. That's flipped. It should be 24% in double support. That's why I paused there for a second. 24%, and our model spends 20%. So we're actually pretty close from this really coarse metric to the human. Now I'll explain a little bit finer metric in a second. Yeah.
The ground reaction forces are really good indicators of whether you're human-like. Do you have a plot of those?
I do have, I have a plot of these reaction forces, because that's what these are. But I have not done comparisons yet, and this is something I want to do. When I say towards, or first step towards, I mean that but it'd be nice to see. This is the ground reaction forces on the toe and the heel.
So the human has that double hump thing, sometimes called the M.
Yeah. The problem is we're very likely not plotting this data the same way that people plot human data, so it's kind of hard. But we do get some humps here, right? That's what this is a hump on the toe. This is kind of, where we get a little bit of a hump on the heel if we kept that going. So we do get some humping type behavior, right?
I didn't say that.
All right. People should have dirty minds at a conference. Control yourselves. All right. So yeah, but that's something we should definitely do. I completely agree. That's something we want to do when we get better data. The problem is the data is really not good enough yet. But I'm going to be getting more data. That'll come up later. All right. Yeah.
The comparison you showed with the human data for percentage, double stance, and so on, is that not set by how you tune your lambda zero controller?
Our tuning does affect. It does affect it. But on the other hand, the tuning is more specific to just achieving walking. Okay? You don't have that. Once you achieve walking, there's sort of a little neighborhood around there that keeps the walking, right? At some point, you tune it too far and you're not going to walk. So we actually didn't tune to have this happen. We just tuned to get the best walking, the most stable walking we could in terms of eigenvalues and things like that. And then we did this after the fact comparison.
With questions included, we want Katya to start in 10 minutes.
All right, 10 minutes. That should be good.
There's questions.
You pretend that's good, right? And then you keep going. All right. I'm right on time, I promise. All right, so let's talk about 3D walking. This will be a little bit faster. So let's go over through the approach. And this is really the main part. And then I'll just kind of show the results and then do a comparison. So with 3D walking, what do? We got good 2D walking. Now, the specific method we achieve it can change. But this technique is generally the same. We start with our 3D biped and we do sagittal restriction. All right? And now we do some sagittal control on the biped, whatever you want. In the case, what we just did is what we're going to use. But you can do other things to get 2D walking. Okay? Lots of approaches to 2D walking. Now here's where the interesting things comes in. Is we actually do some energy shaping to make the 3D biped amendable reduction. Okay? And then we do this hybrid reduction, or geometric reduction, or controlled reduction, or functional Rothian reduction is the technical term. Okay? To decouple the dynamics. And we had a whole talk on that, so I didn't talk about that much, which is great. It's wonderful. All right. So, what that does is decouple, provably decouple the continuous dynamics on the domains. Okay? But that's only true for certain initial conditions. So the last step is we actually do input-output linearization to stabilize the system to the initial conditions where decoupling is true. Okay? And this general scheme is worked out many, many models. We do the same thing every model we consider. So it seems to be a pretty good scheme. The end result is we seem to get 3D walking pretty fast. It took us about, sometimes we can get 2D walking and a week later we get 3D walking using this approach. Like we don't even have to, we don't search, when we do this walking, we never search for initial conditions. We find them starting out with the passive walking and then we translate them. And then for the 3D, we basically start with the 2D initial conditions and it falls in pretty quickly. So we actually don't run a program to do searching. We're kind of that close, which I think says something that we're kind of on the right track. Now, this scheme only works for fully actuated domains, just like controlled symmetries. Okay? So what we do is apply this on the fully actuated domains, and the under actuated domains we do the local controllers that we talked about in the 2D walking. Okay? To break it down a little bit, and I'll be pretty quick here. So first we did the sagittal control. I just talked about this a minute ago, but the end result of the sagittal control was that we got walking. Okay? Now, the reduction controller. Okay? Well, what this does is this uses this functional Rothian reduction. The nice thing is that, again, this has been talked about to some degree. We do some variants on it. But the bottom line is that you do some variant of geometric reduction. I think all these details are not super important. This is the important thing. Okay. So what functional reduction tells you in this theorem is that if you have a behavior of your full order system satisfying this initial condition, okay, then that's equivalent to having a behavior of your reduced system, your 2D walker, satisfying this for all time. Okay? And the key point is that we actually picked this function here. This is up for choice. That's why it's got functional Rothian reduction. So what we've done is we've taken this forward behavior, we've decoupled it completely into the 2D forward walking and the lateral motion. Okay? And the lateral motion we affect directly through the choice of a function. So if you want to, at a high level, kind of see what this means, well, this is like positive definite, so this doesn't really matter. This adds some constant offset, so this is not super important. So basically what you're left with is phi dot equals minus alpha phi. So what are we doing? We're not affecting the forward motion, and we're stabilizing the system upright to some degree. Not exactly upright, but because of this constant offset, but close. Okay? So that's what the reduction does, is this decoupling. But it's only true for these initial conditions. Okay? So the last step is to say, well, let's just converge to those initial conditions. So let's define an output for the system, a virtual output, okay, in line with Jesse's talk here. And we're going to drive it to 0. Well, you can use input-output linearization. We've seen this already. And we can drive this to 0 at some control rate. When we put all these controllers together, we get our final hybrid system that is the feedback control system. So the main result here is that actually we get walking. Obviously what we wanted. Okay? But the important thing is this. We're really merging these different techniques. So the epsilon is the constant for the zero dynamics to converge to the surface. The alpha is the constant for the reduction, how fast you sort of go upright. And the gamma is the constant for the passive walking, essentially, the slope you're virtually walking down. So if you increase gamma, you get faster walking. You decrease it, you get slower walking. Okay? And this is what our limit cycles look like. Let's do a little movie, because everyone loves movies.
Aaron?
Yeah?
Do you have guards on foot roll in the frontal plane?
No. And that's a good point. We have not checked those conditions formally yet. We actually tried, but the computation got us in the way on this model, and we're revamping our numerics a little bit to check all that. But we need to check all that, and we will. That's a very good point. Okay. So this is what the walking looks like if you don't get dizzy watching this. Okay? But it looks pretty good, I think. Now, what does that mean? We can argue that all day, I think, but I think it looks pretty good. Maybe a non-rotating one would be a little bit better.
Can you talk about the degrees of freedom of the ankle?
Let's do a non-rotating one first, and then I'll talk about it. There's 2 degrees of freedom at the ankle. Okay? Not rotating. There's a lateral angle, a lean angle, and a forward angle.
And that impact?
At impact, what?
What's the configuration of the foot relative to the ground?
I mean, so we do add springs to kind of get it all lined up, so we're not doing this multiple point contact thing. But basically, it depends on the impact, but it's something like heel strike. Okay?
But the springs are body reference, not space reference. So if the robot is tipped, how do you keep the impact lined up?
You keep the impact if the robot's tipped.
To clarify what he's asking, maybe.
What is he asking? Yeah.
The foot would technically contact on a point first and then roll.
Yeah, is that what you're asking about that? Okay, that's what I said. I mean, I think, yeah, oh, if you're at the angle, is your body, okay, I understand. We basically, we have such a small angle, we just try to keep everything level. We haven't, and I think that's the short story. Our angle in the lateral angle is very small, okay? So we don't, there would be some minor contact, okay? But the argument is that with small angles, at least, I think, that there's not going to be too many perturbations here on the actual impact dynamics if you were walking flat, if you don't hit at too big of an angle. Now, that being said, I would like to consider this too, but there were complexity issues with doing these multiple point contacts.
And also,
Okay.
you call it fully actuated, but
Not always, but yeah.
But most people, make sure that the 0 moment point or center pressure or whatever is inside the foot.
Yes.
Do you have a check on that?
No, I mean, we don't, well,
We do, right, with the guards. The guards enforce that.
the guards enforce that to some degree, yeah. We need to check it in a couple other conditions. For example, what we were talking about with the rolling. So that's why I say no. We need to double check on that.
Is hip abduction actuated?
You mean in and out, right?
Yeah.
Yeah, no. We're only doing 1 degree of freedom at the hip right now.
So this
Now, we're studying hip abduction in other models.
So this model, it's locked, is that correct?
It's locked, yeah. This model is locked. It looks like there's 2 degree of freedom there, but there's only 1. We want to do abduction, and we've done it with simpler models, but we actually tried to do abduction on this, and it got too complicated. Okay?
So a couple other bells and whistles that you may or may not consider would be the ground friction and the...
Yeah, we need to do the friction cone and all that kind of stuff.
About the actuators, saturation.
Yeah, actuation, saturation, we need to, I mean, there's lots of details we need to consider. There's a whole long list of things we need to go back to check validity after you get these things working, and we've started running down the list to some degree, but we're not all the way there. So let me really quickly then, I'm not going to go on for 10 minutes because that's never good, because that's the main thing I wanted to show. Let me just show this one more slide, and then I'll be done. Is that fair? All right. If we go back and do some comparison with the human data from which the model was derived, okay? This is what we get. And I think this is pretty encouraging from my mind that we started picking the right models. So the main thing that we need to point out is that we're looking at the time in which everything's in contact. The top one is the human, and the bottom one's the robot, okay? And you see that these curves actually are reasonably similar, okay? Except for the knee, because we have knee lock. Everyone got what's going on here? This is the left heel contact, meaning the left heel is in contact with the ground. This is how long it's in contact for the human through the course of the gait. This is how long it's in contact for the biped. It's reasonably close, okay? I mean, this isn't perfect, but you see, at least at a high level, there's the same kind of qualitative behavior of heel, toe strike, and everything like that. And I think that's the encouraging thing. What's that?
You designed it that way, of course you'll...
That's the point, yeah. We designed it that way. But there were some fundamental differences. Our model had
If it
different...
had emerged from a principle, that would have been more impressive, I think.
If what?
If it had emerged from a principle.
Oh, I see. But, I mean, we designed our discrete transitions that way, but our controllers were completely designed by us, right?
That's my point.
But we didn't design them to try to match the data, the controllers.
Yeah, you designed the ordering, but not the
we only just designed the ordering, and even that was slightly different. The controllers weren't tuned to the human data. The masses in the system weren't tuned to the human data. Nothing was tuned to the human data except the ordering of events. So in that case, I would say no, we're not. It's not like we're looking at the human data at every point in time and trying to get it to match up.
There's certainly an argument that could be made in both directions, but
all right,
I think everybody can play that out in their head.
I will leave it there.
I don't think it's
Just
fair to say
one
there was not a principle underlying this. You've got a lot of good theories.
Yeah, I mean, I think, yeah, thank
It's
you.
not ad hoc, this is based on principle.
Yeah, thank you, Mark, yeah.
If the ordering is specified, how much room do you have for various parameters in your control design to get even periodic gates?
There's a lot of room. In controllers and parameters, I mean, well, it's more in the controllers. I mean, because we were designing the controllers on principles, and so without knowing anything about how humans do it, right, except how we think. Yeah, you can close it up and pull it out. And so within the controller design, even then there's there's choices in the parameters that could affect the ordering.
But that's not what I guess you said for the lambda 0 controller, right? The lambda 0, you said you had very
Now no, but our other controllers, we only do that on some domains, right? The other controllers don't take that into account. So it depends on the controllers that we're explicitly studying, right? So yeah.
Chris has a question.
Yeah.
What I tried for.
Oh, sorry. Sorry.
Okay.
All right.
So you have embraced discontinuity.
Yeah.
And that's reflected by discontinuities in your controller.
Yeah.
And for people who've actually tried to implement this on robots, it's very frustrating because either you have to have really good measurements about when the feet are or not in contact.
Yeah.
And in your case, we got to distinguish between heel and toe contact.
Yeah.
Or we have to introduce what Raymer called twilight zones between these states where we're not sure what's going on. So a lot of people say, you know, we should have controllers that don't have discontinuities. They're functions of state and they're smooth. And that way it doesn't matter so much.
Well, I mean,
these are different objectives in these different zones, so.
Yeah, I mean, that's the thing. I mean, in the zones, they're function and states and they're smooth.
Yeah.
But as the zones change, the configuration of the biped changes. So you inherently have to change the controller, even at that level.
That's not true.
The actuation changes.
The have to is not a true statement.
Okay. You may not have to if you pick your control a specific way. But I think if control is tying into the mechanics of the mechanism, it will change as the mechanics change.
Consider walking in mud or on a soft bed.
Okay.
You know, where it's really unclear whether you're in contact or not.
Yes, I agree, but we're not there yet. That's my response to that. We're just trying to get really good walking on reasonable ground. But that's a good discussion. I think we could sit. I'd love to have this discussion for like an hour on these things. So I think these are all good points. We're still trying to understand it better, right?
Do you want to put in a little thing? Okay.
I only wanted to ask one specific question. So if you were to summarize very briefly what you think the advantages are of this method, either in terms of generation of controller or performance outcome, versus the many other ways of generating.
I mean, the advantages I think of this method, are not in terms of performance, because we're not even measuring performance yet. And that's not our objective, is to get fast walking or something. It's really in terms of the principles underlying this to obtain the walking. That is trying to get human-like walking. So the advantages are, at a more specific level, things like 5 discrete domains or 5 phases of walking, which is more than I think anybody else has studied that I know of in a rigorous fashion. This idea of working on these controllers that try to get this human-like behavior and respect the ordering of events. This idea of decoupling the dynamics, right? Things like that. So I think it's the framework, okay? And as I said in the beginning of the talk, you know, if you have a good underlying understanding of the mechanisms underlying walking, okay, you can achieve walking not just on this model, but a wide variety of models, right? You can keep carrying it up.
Can I answer your question for you?
You're welcome to. Yes, I want to hear your answer actually.
With my method, I can find periodic motions that are stable very quickly.
Okay. Yeah.
Is that correct?
Yeah, we can do that for sure. Okay. Yeah, at that level, that's definitely true. That's very fair. Yes, we can find very stable periodic motions in 3D bipeds if you want a very quick answer. Okay.
Let's move on.
Yes. Thank you.